Hi everyone, I hope that you are fine. I'm fine, my family is okay, but I was not able to meet with you. I think I told you already that I have my bathroom is being repaired. Today is the last day they're repairing it, and although I asked them to finish before 5:30, it was not possible. So that's why I have to end up recording this. This is all about inequalities, and I'm going to go ahead and show you how to do this. As, as you can see in this inequality, this expression, this polynomial has to be positive, has to be greater than 0. So first thing I have to do is factorize this. Now we can find what we call the boundary points. These are points or point where x, or the input, is 0 or undefined. Those are the points that I need to find. In this case, either x squared is equal to 0 or x minus 4 is equal to 0. X is equal to 0, that's my first boundary point, or x equal to 4. As soon as I found my boundary points, I'm going to make a number line. Next thing I'm going to do is I'm going to establish my boundary points, and I have an empty circle. Why? Because it's not inclusive. And now I'm going to choose one point from each one of these intervals. Here I'm going to use 5, here I'm going to use 1, and here I'm going to use -1. So now I'm going to check if choosing any point from these intervals, the inequality will be right or wrong. If I plug in 5 on this expression, I will end up with 5 squared, 5 minus 4. But remember that the solution has to be positive. So I'm going to show you what is the answer here, but really what I want to know if it's positive. Because as you can see, I end up multiplying a positive times a positive, and I end up with a positive number, 25. So this interval works. That means that it doesn't matter which number I choose that is bigger than 4, this is going to be positive. If I plug in 1, the first x squared is going to be positive. If I plug in 1 here, I'm going to end up with 1 minus 4, that is negative. And positive times negative is negative. I don't want the answer to be negative. Therefore, this interval is not going to work. Now I'm going to plug in this -1. If I plug in -1, the square will make it positive. -1 minus 4 is going to be -5, negative. Positive times the negative is negative, so this interval is working. I'm done. The solution these are the two intervals that makes this inequality true. Now, in this next inequality, it's already factorized, so you can easily tell what are the boundary points. My boundary points here are x equal to 1, positive 2, and positive 3. So I'm going to go ahead and do the number line. Here I'm going to use 4, here I'm going to use 2.5, 1.5, and 0. These boundaries are included, so I'm going to shade it. And why I'm doing this so I don't forget when I write the solution. So starting with 4, if I plug in 4 on the first parenthesis, I'm going to end up with a positive number. On the second parenthesis, a positive. Third parenthesis, a positive. And the answer is going to be positive. I want this expression to be less than 0, so this has to be negative. or 0, this interval is not going to work. If I plug in 2.5 on the first parenthesis, I will end up with a positive. On the second parenthesis, a positive. On the third parenthesis, a negative. Positive times negative is negative. This interval is working pretty fine. If I plug in 1.5, the first parenthesis is going to be positive, then negative and negative. The answer is going to be positive. So this is not going to work. If I plug in 0 on this parenthesis, I'm going to end up with negative times negative times negative. And that is negative. Therefore, this interval is part of the solution. Here we have a rational expression. My boundary points, if I get 1 here, I will end up with an undefined expression. And here, if I plug in -1, I will end up with 0. So these two works as boundary points. I will end up with 2 plus 1 over 2 minus 1, that is 3 over 1, that is 3. But what I really want to know if it is positive or not. This is positive. If you look at this expression has to be greater than 0, so this has to be positive. Therefore, this interval is working pretty fine. I will end up with positive divided by negative. That is negative, and that is not what I want. I want positive. And if I plug in -2, I will end up with negative on the top, negative on the bottom. Negative divided by negative is positive, and this is working pretty fine. I better have 0 on one side of the equation. I'm going to place this one on the left. I have to multiply this by x minus 2, or turn this into x minus 2 over x minus 2. And now you end up with x plus 4 minus x plus 2, x minus 2. Notice that the x cancel. Now this has to be negative. And as you can see, the only way this can be negative is if the denominator is negative. The numerator is already positive. I will be positive always if x minus 2 is less than 0. Notice that this inequality is less than or equal, but there's no way that this could be equal to 0. Even if x is equal to 2, you will end up with an undefined expression, not inclusive. Section 4.5 is just to practice synthetic division. This is the dividend, this is the divisor, and the divisor has to be always in the form x minus r. In other words, the only allowed coefficient here is 1. If as soon as you have a 2, any number different than 1, you have to get rid of it, dividing by that number. But these ones are already in the form x minus r. Here I'm going to have this number, I'm going to place it here. But it's important that you write the opposite. Now here you're going to write the coefficients of each one of these terms. The x squared, the x, and the constant term. First thing you do is drop these two. And now you're going to multiply this times this. And whatever you get, you write it here. Now you're going to add. Now you're going to multiply these two, 10. Now you're going to add. The last number is the remainder. The solution is given by this expression. You always go 1 degree less than this one, and the remainder you can write it 0 over the divisor x minus 2, the answer. Now you're ready to write the solution using these two expressions. Now this one starts with x to the 5th, then x to the 4th. Notice that the dividend doesn't have the x to the 3rd. but you better write it anyways, otherwise you're not gonna solve the exercise correctly. Now you have the remainder. You're ready to write the solution 1 degree less. Plus 2, and the remainder is 0 over the divisor, x minus 1. Now here we're going to see some application of synthetic division. First one is the remainder theorem. I'm going to demonstrate here what is this remainder theorem about. Let's suppose we are dividing a function f of x by a divisor of the form x minus c. This is equal, it's going to be equal to the quotient plus r over x minus c. Meaning, let's r be equal to remainder. One thing I'm going to do now is I'm going to multiply both sides by x minus c. Let's x be equal to c. That means that f of c is going to be equal to q to c, c minus c plus r. C minus c is 0, so this part will cancel. And now you can see that f of c is going to be equal to the remainder. In other words, once you do a synthetic here, if I want to plug in this 4 inside of this function and know what is the value of y, you can do synthetic and the remainder will be the solution. Therefore, when I write the number here, I have to write exactly the same sign, 25. Therefore, this is my solution, negative 25. So my solution is 0. Now I can say that f of 2 is equal to 0. And this is another one called the factor theorem. I'm going to demonstrate. Now, if the remainder is equal to 0, this is going to cancel, and you will end up with f of x equals qx x minus c. And as you can see, these two are factors. That's what this theorem means. As soon as you have 0 as a remainder, you can then turn this factor of f of x. Use synthetic division to divide and use the result to find the zeros of f. So first, let's see if x plus 1 is a factor. Yes, as soon as you get 0 as the remainder, that means that this one is a factor. So I can express this polynomial as x plus 1 times this polynomial. Now, the question here is find all the zeros. So far, I'm pretty sure that negative 1 is one of the zeros. In order for you to find the rest, you just factorize this part. And now you can tell that the other two zeros are positive 2 and positive 1. I got these two zeros with these ones. If x equals 2, you end up with 0. If x equals 1, you end up with 0. If x equals negative 1, you will end up with 0. So it's very important to differentiate between the zeros and the factors. Solve the equation given that 2 is a zero of this polynomial. One thing you must know is that if a polynomial is degree 3, we must have at most 3 solutions. One of the solutions is given, so I have to find the other 2. I'm going to do synthetic with this given solution. Notice that I'm using the same sign because this is not a factor. This is not x minus c. This is just a number that I want to plug in. So this confirms that 2 is one of the zeros. Now I'm going to keep working with these ones. Just factorize, and I'm ready to find the other two zeros. So this confirms what I was telling before. Every time you have a polynomial, you can have what we call the rational zeros. These are nice numbers like negative, positive fractions. You can have what we call irrational zeros. Now you have to notice that in these polynomials, they always comes in pairs. By the way, they are called conjugates. And the same with the complex imaginary solutions. They always comes in pairs and they're always conjugate. Just for you to remember, what is a conjugate? This is the sign that changes. The first term never change. It's just the second term that change. So again, the complex numbers always comes in pairs and the irrational numbers always comes in pairs. Here we have what we call the rational zero theorem. With this theorem, you can have an idea how many out of all the zeros or solutions of a polynomial, how many or which ones are rationals. I mean, these nice numbers. Rational zero. Let's suppose we have this polynomial. This polynomial is degree 4, as you can see. So the rational zero tests do the following. You have to do on the numerator, you have to write all the factors of the constant term on the polynomial. And on the denominator, you have to write all the factors of the leading coefficient. So the factors of 8 are plus and minus 1. Plus and minus 2, plus and minus 4, and plus and minus 8. And all the factors of 3 are plus and minus 1 and plus and minus 3. Remember, you have to consider both because in the case of 8, for example, negative 2 times negative 4 is equal to 8. All the possible rational zeros are, these are all the possible rational zeros. As you can see, there's a lot. Here we have 2, 4, 6, 8, 10, 12, 14, 16 possible rational zeros. Let's go ahead and show you how to do this exercise. First, we have to list the possible rational zeros. Now we have to use synthetic division to test the possible rational zeros and find actual zeros. How can I use synthetic division? How can I know it's a zero? If once you try with a number, you end up with remainder 0, that tells you that that is a zero of that polynomial. And then it says use the quotient from part B to find the remaining zeros. Factors of the constant, factors of the leading coefficient. Now I'm going to try with synthetic division. As soon as I find the first zero, then I can stop and continue factoring. Negative 6, 0. As soon as I get 0, that tells you that this is one of the zeros. Remember, this is degree 3, so you have at most 3 solutions. In order for you to find the next 2 solutions, you can just stop here and work with this expression. And this gives you the other 2 zeros. Therefore, you can say that the zeros are 1, positive 3, and negative 2. Factors and x minus 1. Remember, this factor came out of this 0. As you can see, 1 is not a 0 because you don't get 0 on the denominator. Now let's try with -1. -1 is not a 0 because I must get 0 as a remainder. Yes, I found my first 0. But now remember that this one is degree 4. You must get at most 4 solutions. So I have 3 more solutions left. Now I'm going to continue with this row. As soon as I finish the first one and I got 0, you don't have to continue with the original row. You can continue with this row as soon as you get the first 0. There you go. Now I just found the second 0. And now it's easier to just stop there and work with this expression. I can turn this expression, but as you can see, there's no way you can factorize this. So I can find the other two zeros. Could be either complex or irrational. Add that. This gives me the other two zeros minus square root of 2. And the last section is the complex zeros, or the fundamental theorem of algebra. This one is confirms what we learned on the last section, meaning the same, like if you have an imaginary or complex, you must get the conjugate, or if it's irrational, then you need the conjugate in order for it to be the 0. So here, for example, find the remaining zeros of a polynomial function f whose coefficients are real numbers. So this one is degree 3. So far here I have 1 and 2 zeros. But I know that this is complex and the conjugate is also a 0. So I can tell that the zeros are, this one is degree 5 and the given zeros are 1, 2, and 3. But these two are complex and the conjugates are also zeros. So the zeros are, this one is degree 6 and the zeros given are 2 plus I, negative 3I, and 0. So far here I have 1, 2, 3, 4 zeros, but these ones are conjugates. So the zeros are, and these examples, find a polynomial function having leading coefficient 1, least possible degree, real coefficients, and the given zeros. So here we have the given zeros. But I know that if I is a 0, the conjugate is also a 0. So the zeros are negative 3, 2, I, and negative I. Now I'm going to turn these zeros into factors. This negative 3 came out of the factor x plus 3. This 2 came out of the factor x minus 2. This one came out of the factor x minus I, and this one came out of the factor x plus I. Now, in order for me to find the polynomial, I just have to go ahead and multiply all these factors. This is x squared plus x minus 6 times x squared plus 1. Now you can combine. This is the final expression of the polynomial. X minus 3, that's where this 3 came from, minus 1 minus square root of 2, and this will be x minus 1 plus square root of 2. Go ahead and multiply these two expressions first. They are conjugates, so I'm sure that some middle terms will cancel out. Notice that a lot of things will cancel out here. These two will cancel out the same as these ones. And now you can just finish up multiplying this binomial times this trinomial. And this is the final answer. One thing I can show you to solve this easier is as soon as you see conjugates, these are difference of squares. I can express these two expressions as the following. Now, in this way, you can avoid multiplying a lot of expressions here. So now you just work with this part. This is x squared plus 4x plus 4. This is -1. And in this case says use a graphing utility to find the remaining complex zeros of each polynomial function. Number 7 gives you one of the zeros, 2i. You can tell that -2i is the second zero. And then this is degree 3. So with the graphing, you can find the last zero you need. Once I enter here the function, here's a graph. And then here you can tell that the next and last zero is 4 because the line is passing through 4, and that will give you the remaining zero. Okay guys, in this case you just have to graph each one of them. I'm going to go ahead and show you with number 8. So here you can tell that the root is 1/2 and -3. -2i, 2i, 1/2, and -3. And the same with this one. 3 minus 2i is one of the zeros. 3 plus 2i, and then this is degree 4. You need 2 more zeros that you can find once you do the graph. Okay guys? So this is all about those sections. I wish you the best.